So the next speaker is Yu Yi. He is Associate Professor of Electrical and Computer Engineering and the 2024-27 Copenhagen Fellow in the Engineering School here. His research, as you've already heard, is on quantum and classical applications of integrated photonics through leveraging optical resonators and frequency combs. And he is working on putting these techniques onto chips. So without further ado.
Say all now. Okay, yeah. Thank you for the introduction, and then thanks, Stefan. And
Bye.
Yeah, and Olivier for those amazing talks. So I'm going to talk a little bit more on the hardware side, engineering side, and then to show you what has been happening in the past few years as a trend, right, of the how to realize, bring those theories and then those schematic to a manufacturable chip. So yeah, I changed the title last night. Okay, so so I want to start again with a little bit of the basic that what quantum computing or what quantum science and technology basically want to do, right? They want to use quantum mechanics to achieve tasks that are not possible with classical mechanics. And then those include computing, communications, and sensing. And then for communication and sensing, there are already amazing things that have been, put into, I wouldn't say commercialized, but put into real use. And then computing would be the next important thing, of course. And then so kind of revisit this again is that what's so special about quantum computing? If you look at a system with n bit, right, in classical computer, like in your phone, those n bit, okay, binary bit, they can represent 2 to the nth possible configurations, so 2 to the n possible different information. But at each given time, each of this bit only have one state, and thus you only have one, even though you have n bit, you only have one piece of classical information at a time. And then as Stefan has introduced us, right, you have superposition and entanglement. So for a quantum system with the same n qubit at this time, then you will get 2 to the nth possible state, and then they could coexist, right? It's like superposition entanglement. So for this quantum state, you actually need 2 to the nth coefficient just to describe their superposition. And this is extremely powerful, this exponential law. We can give, and then by superposition, you can think about as the Schrodinger's cat, which I'm sure a lot of you have heard of. And then the n qubit superposition is n cat fighting each other, and then in a quantum world, right? So how powerful is this, right? So if you think about 300 binary qubits, which is not that large, okay? In a classical world, right, we all have billions of transistors in our phone, and then you have 2 to the 300. You need 2 to the 300 parameters to just describe this quantum state. So imagine you have a big molecule with 300 atoms, and that number approximates to 10 to the 90th, right? So you have 90 zeros following 1. It sounds doable, but then if you actually run the number, it's more than the number of atoms in the entire universe. Okay. So if you think about it, that creates a big problem. Is that if you want to brutally solve a molecular interaction of, or molecular formation of 300 atoms, you just can't with classical computer because you run out of memory. Okay, and then so they just showcase you that there are definitely a lot of problems and important problems in material science, in medicine, in biology and chemistry that you can't use classical computer to brutally solve the answer. So quantum computer can provide that path, right? Because your system itself is quantum, and then you can conveniently simulate that. And then of course there's many algorithms that you can use quantum computer to solve the classical problem as well. Okay, so with that being said, then we know that one important thing for quantum computer is that you want to scale up, right? You want to scale the number of n. The more qubits you get, the exponentially more power you get, okay? So with that, and then there are many different platforms, right? There's the transmon qubits, invented at Yale, and then later Santa Barbara, and then acquired by Google. And then the photonic type, there's USTC in China who did those satellite teleportation work, and then UVA, Tokyo University, and then two giant startup company. They're now in $1 billion. So I think that's still called startup unless they go public. And then there are trapped ions. These are very cool. IonQ, Maryland, and NIST, right? Each of these tiny dot are trapped ion. So there are many ways to implement this. But then you always have this problem is that it's difficult to scale up. Okay, it's difficult to scale up to 300. I just said 300 is not that large, but it represents more. You have more coefficient than the number of atoms in the universe. But getting to 300 is actually very, very difficult. There are different technical reasons for different platform. And then, but then if you oversimplify it, one kind of higher law that preventing you getting there is the compound yield. If you have 99% chance of making one qubit work, which is excellent, right? You can publish wonderful paper about it. Then if you build 100 of them, then only 37% of it work. 1,000 of them, then 0.01%, and then 10,000 of them, you're going to use all the sand in the world, but then you can't make that much semiconductor wafers here. And then people keep saying, if you look at IBM and then Google, they keep saying you need millions or billions of qubits, right, to build error-corrected quantum computer. And we're going to run into big trouble there. And so in this kind of compound yield law, is there an escape from that, right? So can you just have a few devices and then create many, many qubits? And then Olivier's work already demonstrated that, but then I'm just going to introduce this in a different angle, right? So if you can use a few devices and then generate many, many quantum modes of qubits, then in a way, you kind of work around that compound yield issue. And then, of course, you want it to be able to be compatible with integrated photonics, with the technology that can be massively producing computing units. So we need photonics, integrated photonics. So kind of to walk through what we mean by using photonics, you can use one device and then generate so many qubits or Q modes. The concept is actually very sophisticated in classical world. The internet, right, using fibers, and then you send information through lasers. And those are actually using the same concept, is that in one single fiber, you actually have multiple wavelengths, okay, all carrying information inside. So each fiber itself, I think at this time, maybe hundreds of wavelengths using it. And then so you don't have to deploy hundreds of fibers, but just hundreds of different wavelengths, very nice colors, okay, inside your fiber, and then you can do that. And then this is kind of the same thing, okay, in quantum, is that if you can leverage that, if you can have your device supporting, millions or thousands of millions of different wavelengths and have them behave quantum mechanically, then it's possible, okay, that you can bypass that yield issue, right? You can have a few devices, and then you can generate thousands or even millions of qubits or Q modes. And then here's just an example of a Fabry-Pro cavity, optical cavity that light bounce back and forth inside, and then you will have, you will support different wavelengths of frequency when it's constructive interference. And then even the simplest device that people learn in like undergrad level in optics, right? These are supporting thousands of different frequencies, and this is kind of example of how you use photonics to create lots of qubits or Q modes. Okay, so then we look at this Fabry-Pro cavity and then kind of see how it looks like in the quantum world. So in classical world, you will see, okay, this cavity, light can trap inside at certain frequency. But then if you do a quantization of it, then all these modes, they look exactly like a harmonic oscillator. They're like oscillating electromagnetic field inside, but then they act like a mechanical oscillator. So even by just building two mirrors and then have light bouncing back and forth, you already have thousands of quantum harmonic oscillator inside. Those can be used as qubits or qmodes. And then of course, if you just have those, they're not that interesting. Okay, they're in the vacuum state. So then what you want to do is that, as Olivia has introduced, right? The important thing is you want to have entanglement among them. And then so this is again from kind of the configuration same as Olivia's slides. It's that you have light going in, and then they have interactions among them, and then you generate photons. Then you can entangle light of different colors. Okay, and then the way, depending on how you configure your experiment, you can entangle different color with different. You can entangle different colors together and then form complicated states for your computing. And I want to spend a little bit of time to kind of talk about how you use that for once you have entanglement, how you use that for computation. So I'm not going into any algorithm, but just simply on a high level, okay, what computation means, right? Computation means you use a piece of information to change another piece of information. So if you look at teleportation, if two states are entangled, right, and then we know if we measure one of them, it will change the other, right? It will change the other teleportation. So that's actually very, very close to the concept of computation, right? You're just one step away. So, so this nice paper, like back 20 or 25 years ago, right? They figured out that you can use teleportation to build a universal quantum computing. Is you have different states entangled together, and then you measure some that change the state of others. And then if the state change is the way you want it to change, right, then that's a computation. If it's not the way you want it to change, that's a random number generation. Okay, so here is an example of how you can do controlled NOT gate, which Stefan introduced. Right, you just do have the entanglement in a special way, T-shape, and then you do measurement on two of them, and then apply unitary single qubit gate on others, and then you can have a controlled NOT gate. Okay, so yeah, so for photonic platform, then all you need to do is that you generate entanglement using optics, and then you do measurements that those implement the computation. Okay, so the generation of entanglement and then the measurement or detection of the light is kind of the two critical elements. I want to just highlight some of the progress key progress in the past probably 10 years. And then of course, the first is from Olivia Vista's group that's showing that this concept of using different frequencies and then having them entangled together actually work, right? Generating 60 modes, actually generating probably 3,000 modes and then measure 60 of them. This is actually, if you think about how much, when Google made the first, big paper, it's 53 qubits, and then this is 60, right? So this is quite amazing achievement for photonic system. And then also, as Olivia have already mentioned, from University of Tokyo, people have generated 1 million Q-mode entanglement using time domain multiplexing. Like your laser can keep emitting light, and then you can entangle the light emitted at different time. And then this way you can generate probably the most amount of entanglement. But then, of course, it's difficult to use them for computation because you need to separate light, separate light, route light generated from different time to different places for detection. So we think probably a combination of these two will eventually, give you a viable path moving forward. Then, of course, there's the brutal way. It's spatial domain multiplexing. You simply build 100 of the same thing and then put them together. And this is the famous paper from USTC China, is that they have, I think, 25 or 50 of Olivia's squeezing generator, and then have a full room of interferometer, and then it's very fancy experiment. And then they demonstrate the quantum computing advantage. Okay. So with that being said, I want to introduce a little bit of our work here. Is what exactly do I do here? So the main goal is to make the transition from bulk optics, Olivier's lab, and then into integrated photonics. And then, this happened actually before I joined UVA. It was during my interview, and then Olivier has started convincing me, to work on this before I even had an offer. So, so if I ended up somewhere else, I would steal Olivier's idea and then also do this. So my background is in integrated photonics, okay, all these small micro resonators, and then also frequency comb, but in the classical domain. So a collaboration with Olivier is a very, it's a very, very good combination. The idea here is that although photonic system, you can use one device to generate thousands of qubits or qmodes, but eventually you need to process them, right? You need to measure them, you need to change them. And then in free space optics, then that means thousands of mirrors or millions of mirrors, okay? And then that might not be sustainable, okay? Might not be sustainable. Somebody might try it, but then we don't think it's sustainable. In comparison, this is the chip in our labs, and then this is 1 cent coin, and then in each of this device, you can zoom in, and then there are hundreds of components on it. So with a footprint smaller than the size of a mirror, you can actually have hundreds of thousands of components, and then that's where the technology should go if this one day become really possible. So I'm just going to show some fancy pictures of the chip because they're good look. They look very nice. Also, it took us a very long time to take good-looking pictures. And then these are the chip, Andreas Beeling fabricated. And then on this side is the quantum source. On this side is his detector. So we try to have entanglement generated and then measured on the same chip. And then also this is not really a quantum, but then this is probably the best looking pictures in our lab, right? Ascent, and then this is a chip that you can generate squeezing, and then quantum entanglement, and this is Andreas photodiode, and then you zoom in, all of these are very small, and this is from our collaborator. I just don't want to cut the image, but then, okay, we have collaborators from Santa Barbara sending us devices. And then I want to kind of just briefly talk about what this device really is. It looks like just a ring, okay? And then the reason that we use a ring is that this ring can trap light inside and then go circle, circle around, circle around. And then in this way, when you trap light inside, and then the power keep building up, right? You keep sending light into it, and then the power keep building up. And then eventually you can, for example, input 100 milliwatt, which is what you can achieve with commercial lasers. And then inside the little ring, you can get 10 kilowatt, which is weapon level. Okay, so so really you can do a lot of fancy experiments with, I would say, college allowed equipment, right? And then generate fancy experiments. And then later I will explain a little bit more on this. Okay, so the next point, right, when you try to miniaturize things, when you try to go small, then of course you wonder, how's the performance, right? Is it really good? Are you giving up are you compromising something? And then this is part which is quite interesting, is that if you guys think about the phone or the computers you guys use, right, the transistor size actually go down probably more than 100 times since 20 years ago, and then your phone and your computer keep getting faster and more energy efficient. And there's a good argument in electronics is that the smaller your transistor is, the less time it takes for electron to travel from one device to another. Also, that means faster speed and also lower energy consumption. Here we can make a similar argument, is that smaller is actually better for photonics. And then the reason is this, okay, for the photons to create entanglement, or for anything to create entanglement, you need those two parties to interact with each other. Right? You have to have two Schrodinger cat fighting each other instead of just sitting there. So then when you have things really miniaturized, then light is being trapped inside. And then if you think about if you go one round trip, you interact once. And then now going one round trip is just much, much shorter time. Okay, so this is an extreme example by using Olivier's cavity size, which is already very small, and then comparing to the smallest resonator in my lab. and then the volume is actually 1,000,000 times smaller. Okay, that means that the interaction strength, if everything else is the same, then the interaction strength is 1,000,000 times stronger. Then you can say, okay, then I can lower my laser power by 1,000,000 times to generate the same entanglement, or I can use some materials which are more friendly to other things, but then has smaller interaction. So it really opens up a lot of possibilities when you have small device. Okay, so far we haven't found any deal breaker for making things small. What's the sacrifice? Okay, hopefully we never find any. But then, yeah. So so with these small resonators, what we did. So I think I'm a little bit kind of too optimistic. I started this during my tenure track, and then I remember multiple professors at other university tried to convince me not to do it. Some at Yale saying that, oh, this is going to ruin your tenure track, but then I think I have the help from Olivier, so things fortunately go very nicely. So this is the first experiment we did back in 2021. Actually during the pandemic, so students actually work at night, and then to have the shift, and then so this is a kind of the same thing as what Olivier has shown. Is that you basically see where vacuum is, and then you can show where entanglement is, and then we just show a little bit entanglement using a small ring cavity from our lab. And the critical part that make this paper interesting is that we show the concept that Olivier created earlier, is that you can use one device and generate many quantum units. And then in this case, we have one small microresonator, and then we measured 44 quantum modes, which is quite impressive. And then later we moved to more integrated platforms. And then these are the chips you can see, okay, coin size, and then this is the actual resonator, and then light actually circle inside. And then this is just a more integrated system, and then you can put it together with lasers and detectors later, so that's why we picked this platform. Also, the chip is fabricated at commercial foundry. Okay, so this is also something means that it's more expandable later. And then in this case, we measured 30 quantum modes, okay, generated from one device, which is not bad at all. Our goal, of course, is to keep pushing the number. Of course, we want to go to 100 and even more. This is 2023, and then fast forward 2 more years to now. Andreas Billing, Professor ECE, and I were working together to put more components to the chip. And on the left-hand side was the entanglement source you see. Sorry, I think I had the auto run going. On the left is the entanglement source you have seen in the previous slide, and there's some other filter and then combiner on top, and then eventually end up with the detectors Andreas group fabricated. And then because every photon, its destiny is being detected. Okay, so this is still ongoing optimization, but then this is the first chip that actually worked. And then so we hope that this really tell people that the concept of moving to integrated photonics will work equally well as the free space. Okay, and then a little bit touch on the possible future roadmap. As any quantum system, okay, we want to go with more and more qubits. Okay, we want the error rate to be less and less. And then at the moment we're roughly here, and then want to go there. Okay, and then I think UVA has the strength to do that. Olivier and I are working on the frequency comb, and then Andreas Billing and Joe Campbell and I are working on the integrated photonics, and then of course Joe Campbell and Andreas Billing are the world expert on photodiode. So we think we have the elements to make this work. Of course, it would be better if we have a laser person, right, to kind of power the whole system here at UVA. Okay, so at the end, I want to thank our sponsor, SF, DOE, and then also DARPA. And then this picture was from 2 years ago, and then also the Olivier Joe and Julius are photos together, working together. Okay, and thank you.
We have time for a few questions.
Yes.
You guys mentioned one node, and I guess I think it's still Photonics.
Yeah.
How K-based quantum can even like touch that, so only touching three orange. So like it's still continues very closer to having development on a computer than super quantum.
I would say continuous variable quantum computing is not closer, but then because at this point you have the architecture, you have individual components. There's some demonstration of gates, and then even I think quantum advantage with boson sampling. But the circuit base, well, it's not really circuit versus continuous variable. It's the hardware, right? It's the superconducting qubits, and then Hurry trap iron. They they had the 10 or 20 years ahead in the research. So that's what it is. But then I'm quoting someone from Caltech. I don't want to say the name, but then is that the current technology is need to be 1 billion times better, and then we're 10 times worse. So we just need to be 10 billion times better than now. If you think about if you want to improve 1 billion times versus 10 billion times, you don't really care about that time difference. Yeah.
Yeah, I think you were showing some of the plots where you're generating different quantum flows.
Yeah.
Compared to what you're showing with lasers, you seem to have some regions that have a lot of noise.
Yeah. So, do you mean like something like this, like some of this going away? Yeah, this is actually the fun part in integrated photonics is that there are actually multiple spatial mode inside the cavity that can interact, and then this is where they interact, and then they you can think they damage the quantum property. So we have sort of resolved it here with the better design, and then different material, better design. You can see that there's never a mode that go completely bad, right? Just closer is probably a little bit better, and then slowly fading away when you're further away because of the measurement capability. But then you never had those bad modes anymore. Yeah. Yeah.
Okay. You were showing that photon number resolution. Is that what you were showing on the next page? That device up above, is that?
No. This is we hope. Yeah, but no. Yeah, this is measuring the field of the photons. Like the electrical field of the photons, homodynamic detection, and this can operate at room temperature. And then so this is one of the necessary part for photonic quantum computing. Not only you need to count numbers of photons, you can think about counting numbers of photons is measuring the energy level, right? But you also want to able to measure position momentum, and those are using these detectors.
Noticed for photonic quantum computing, like we talked about like the Q modes and how we have so many Q modes,
Yeah.
and they will like the numbers more massive than
Yeah.
discrete like qubits. So can you do like very exciting like I guess experiments with quantum simulations, like you want to create like a robust quantum system, say molecule like caffeine or something.
Yeah, I would think so, but I'm not expert in those, so I think Olivier later can address that.
Well, we're at 2:40, so let's go ahead.